Good evening, Mr. Metzler, or anybody watching this just to get any help with physics. Um, Today, I will be doing the one of the free response questions on the 1976 um, physics AP exam, and this is the question 1976 E1. So, for starters, what we know about this is that this is a solid metal sphere of radius r that has a charge 2q. A hollow spherical shell of radius 3r is placed concentric with the first sphere and has a net charge of negative q. So on the diagram below, it asks us to make a sketch of the electric field lines inside and outside of the spheres. So what we have to take into account first is the charges. The magnitude of the charges. The charge on the center of the sphere is 2q, and the charge on the outside is negative 1q. So the magnitude of the electric field on the inside is going to be twice as great as the electric field on the outside. So we're going to represent that with twice as many lines. And they are all going to be facing outward because the charge on the inside is positive while the charge on the outside is negative. So I'm going to draw those here like so. And then half as many on the outside, so I'm just going to draw 4. And that's all you need for problem A. Moving on to problem B, use Gauss's law to find an expression for the magnitude of the electric field between the spheres at a distance r from the center of the spheres. So this is asking us to use a Gaussian surface in this area here to find the electric field there. And because this is a spherical object, it makes sense to use a Gaussian surface that is the same shape. So for starters, what we know is that flux is equal to the integral of E dot dA, which is also equal to the charge enclosed in our Gaussian surface over epsilon naught. And then this is an easy integration. The E comes right out because it is constant, and we just integrate dA to A. So EA equals the charge enclosed over epsilon naught. And because we are using the same kind of shape as the object itself, we're going to use the surface area for a sphere. So that is E times 4 times 4 pi r squared, which is equal to q in over epsilon naught. And our charge enclosed here is going to be 2q because that's the charge enclosed inside of the Gaussian surface. So E equals 2q, which is positive, and since E is by itself now, we're just going to put all of that over 4 pi r squared times epsilon naught. So 4 pi r squared epsilon naught, and we have a constant which is 1 over 4 pi epsilon naught, and that's k. So we can make this equation just a little bit simpler. E equals k 2q over r squared. And that's our final answer for the electric field inside of the sphere, from r to little r to 3r. So question C asks us to calculate the voltage between the two spheres. So we know that voltage equals the integral of E dot dr And we have our we already have our we already have our electric field from R to 3R. So we plug that right in. V equals the integral of K 2Q over R squared times dr. And then K 2Q, K and 2Q are constants, so we could take those right out of there. So V equals K 2Q times the integral of 1 over R squared dr. And that just simplifies, that all simplifies to V equals 2kq over r from r to 3r, which equals 2kq over r minus 2kq over 3r, which equals 4kq over 3r. And that is our final voltage from R to 3R. Now the last question asks, what would be the final distribution of the charge if the spheres were joined by a wire? So there will no longer be any charge on this center sphere because it will all go to the outer sphere. This means that the outside will have a charge of positive Q, and that's because the charge flows from positive to negative. So our answer for that is simply no charge on the middle and positive Q is our charge on the outside. Alright, thank you for joining me for solving problem 1976 E1. Yep, that's all. Thank you very much.